We're going to finish up our discussion of single number summaries now. Remember that single number summaries try to capture some aspect of a histogram with a single number. So we have the mean, the median, and the mode that all try to tell us what is a typical value in this distribution. We have measures like the standard deviation, the variance, and the interquartile range that tell us how dispersed or heterogeneous is a population. Now we're going to capture a few more. So one of those measures is called the coefficient of variation. The coefficient of variation on page 52 is a measure of relative dispersion. So it says how much dispersion is there relative to the mean. It's simply the standard deviation divided by the mean. Let's go over to the sketch pad and I'll give you a little example to illustrate why we would care about relative dispersion as opposed to absolute dispersion. Let's say that we are tracking some stock, and let's say that that stock has a mean closing price of $100. And let's say that the standard deviation of that stock is, say, $5. Now, if we work under the additional assumption that that stock has a normal distribution in the closing price, we can draw a graph of it that looks something like this. So on the average, the closing price is going to be 100, and then 95% of the time we're going to be within 2 standard deviations of the mean. So here are 2 standard deviations of the mean. 95% of the time we're going to have between 90 and 110 as the closing price. Now consider another stock, and let's say this stock has a mean of only $10, but the standard deviation is also $5. And if this stock is also normally distributed, then the mean is going to be 10, and 95% of the time we're going to be between 0 and $20. The standard deviation is often used as a measure of risk, but in such a case, it's really not capturing risk, because certainly the second stock is much more risky, because some of the time we might lose everything, some of the time we might double our money, whereas in the top stock it fluctuates much more closely to the mean. All right, so this hopefully motivates why we would want to look at the coefficient of variation to measure relative dispersion. So the coefficient of variation here is going to be the standard deviation 5 divided by the mean, which is equal to 5%. The coefficient of variation down here, on the other hand, is going to be 5 over 10, which is 50%. Coefficients of variation are often expressed in percents, and in this case we see that this stock is considerably more risky, has a higher relative dispersion than the first one. All right, so that's the coefficient of variation. SPSS, by the way, does not compute the coefficient of variation for you. You have to find the standard deviation and the mean using, for example, Explore, and then divide them with your pocket calculator. Here are 2 other measures that capture some aspect of a histogram. One is called skewness. So skewness attempts to capture the skewness of a distribution in a single number. The interpretation is quite simple. So 0 means symmetrical. Negative values indicate left skewed. Positive values indicate right skewed. So let's go back to page 38, where we had some pictures of histograms. I've indicated the skewness below these histograms. So both the normal and the uniform have a skewness of 0 since they're symmetrical. The skewness of this distribution, the right skewed one, has 0.7. The left skewed or negative skewed distribution is minus 0.7. So values that are negative indicate a long left tail. Values that are positive indicate a long right tail. If we go back to SPSS now, remember we computed the skewness of that, where was that? The down payment example. So let's look at the down payment example. And recall that the down payment example was very right skewed. Well, if we go back down to Explore, so we've already computed this, in a previous video, you're going to see a skewness of 6.5. So the fact that it's positive indicates we've got a right skewed distribution on our hands. The magnitude of this skewness is also interpretable. Bigger means more skewed. So a skewness of 6 is really skewed. Recall, going back to the course packet, this thing was just 0.7, so that's just modestly right skewed. I'm not going to give you the formula. If you're interested in the formula, you can get it on Wikipedia. It's a function of how far the mean is from, each observation is from the mean cubed. So let's go back to, I believe it was page 52. The last measure of describing a distribution is called kurtosis. Now, kurtosis tells us the peakedness or tail heaviness of a distribution. Kurtosis is calibrated so that the value 0 is normal. So anytime you have a normal distribution, normal shaped tails, the kurtosis is 0. You don't need to know this, but that's called a mesokurtic distribution. Whenever the tails are thicker than a normal curve, for example, the tails of a uniform distribution were thicker than those of a normal distribution, you have a negative kurtosis. So let's go back to page 38 and look at that uniform distribution. So the kurtosis is minus 1.2 because notice these values out in the tail are much more common than you would expect with a normal distribution, which has a kurtosis of 0. Those are called platykurtic distributions. Again, I don't care if you know that term. The other possibility is that you have thinner tails than a normal distribution. So consider this distribution off to the right, where I like to call this the Washington Monument distribution. You have one tall peak in the middle, and you have extremely thin tails on either side, much thinner than you would expect under a normal curve. Such a distribution will have a positive skewness. You see this one has a positive kurtosis. In this case it's 27, and that's called leptokurtic. If you go back to SPSS for a second, you'll see that the value of kurtosis is displayed just below the value of skewness. The value of kurtosis for that down payment example is 105, which is pretty extreme, pretty large. Okay, so skewness and kurtosis are the last two measures, single number summaries that describe a distribution. So the point here is that all of these measures will describe a variable. So you can look at a histogram, or equivalently, you can look at these various single number summaries to get a picture of what's going on with the variable. I need to now introduce some new notation. Up until this point, I've assumed that we've been talking about a population. So whenever we talk about a population, we're going to use the following symbols. Big N is going to be the size of that population. How many elements are there? So how many sampling units are there in this population? Is big N. We're going to use Greek letters usually for statistics for for these univariate descriptive statistics of a population. So mu is the mean and sigma is the standard deviation. In real life, we don't tend to have censuses, though, so therefore we don't know mu and sigma. Instead, we're going to be using data from a sample. Whenever we have data from a sample, we're going to use slightly different notation. So little n is going to be reserved for the number of elements in our sample. X bar will refer to the sample mean. And S squared is going to be the sample variance. The square root of that S will be the sample standard deviation. Now, the sample mean, X bar, is computed in exactly the same way as the population mean, which is mu. We just add up the values and divide by n, the number of values that we've added up. So there's really no conceptual difference or no computational difference between the sample and population means. There's a slight difference in the way we compute the sample variance. If you remember, the population variance was the typical squared deviation from the mean. We added up the deviations from the mean, we divided by big N, which gave us the average or typical deviation from the mean. With the sample variance, again, we're going to add up the squared deviations, but we're going to divide by n minus 1 rather than n, which always strikes students as being a little bit weird. Statisticians universally agree on this, that we're going to divide by n minus 1 whenever we have a sample a variance. The reason for it we'll discuss when we get to chapter 7. I'll give you a one-sentence explanation at this point. With this denominator, if we could average across all possible samples, consider all possible samples, compute the sample variance of each using n minus 1 in the denominator, then on the average we would get the true population variance. If we were to divide by n, we would not get the true one. We would be slightly biased. All right, and that's why statisticians prefer the n minus 1 denominator. All right, so most computer packages are going to report S rather than sigma. That includes SPSS and Excel. If you use the stdev function in Excel, you're going to get S rather than sigma. Okay, one more topic. Up until now, we have assumed that we have all the values in our sample or in our census, and we go off and we compute the mean and the variance. Sometimes we want to do this from a frequency distribution rather than from the raw data, the individual values. So let me give you a little example. Let's return to that question on page 29. How was your overall experience at the California Pizza Kitchen? And here was the frequency distribution. Let's find the mean. Now, the mean was reported to be 4.29. The variance was 0.5159. Now, where do these come from? Well, if we wanted to compute the mean, we would have to add up all the values. Well, we have 27 ones, so it's 1 times 27. We have 178 twos. We have 1,779 threes. So we'd compute all these products, then divide by the total number of values, which is 16,010. Well, we could just compute the products and then the sum, then do the division, but we could also do the division first. So I'm going to divide 27 by 1610. What is that? Well, that's just the percent. So 1 times 0.2%, then 2 times 1.1%, which is in that percent column, all the way through 5 times 43%. So in essence, we're giving 43% of the weight to the value 5. We're only giving 0.2% of the weight to the value 1. This is an example of a weighted mean. So normally we're giving equal weight to every number that we're averaging. So if I just computed the simple average of 1, 2, 3, 4, 5, each number would get 20% of the weight, or 1 over 5. With a weighted mean, we want to give different weights. So we want to reflect the fact that 5 is much more likely to come up than 1, so therefore we give it a whole lot more weight. All right, we can do the same thing with variances. Remember, the variance is just the typical squared deviation. So we're going to give 43% of the weight to the deviation that 5 is from the mean, the squared deviation that 5 is from the mean. We only give 0.2% of the weight to the deviation of 1 from its mean. And you'll note that we get exactly that variance. I point this out because this is a topic that's going to be coming back when we get to chapter 7, when we get to the mean and the variance of random variables. We're going to be using exactly the same formula. So the whole idea is you use these percentages to determine the weights, how much weight to give to each of the numbers. So it'd be worth you practicing this in preparation for chapter 7. It's a little bit easier to grasp what's going on now in chapter 5 than it will be when we get to chapter 7.